Hello dear. In this video, we're going to see an example for genetic algorithm. So genetic algorithm is an optimization algorithm and that is based on the evolutionary algorithm. So here, the steps involved in genetic algorithm is like the first step is to select the encoding type. So as we discussed in the previous video, like all the chromosomes, like all the solutions here are going to be represented in terms of chromosome structure. So for that particular problem, how you're going to represent the chromosomal structure? So that is called encoding type. Okay, the way in which we select a encoding method, like the way in which we are going to represent the solution in terms of chromosomes, that is called encoding. That is the first step here in genetic algorithm. So the next step is like once after selecting the encoding type, next we are going to choose the population size. So here we're going to operate with some set of solutions. So the populations, the set of solution, the number of solutions that we are going to operate at a time. So that is called population. So initially we have to choose the number of populations we are going to operate. So that is going to be a standard value for all the iterations. So next one is randomly we are going to choose the initial population. So out of the existing solution, we are going to choose some random solution, not the best one. We don't know whether it is the best one or not. Randomly, we are going to choose the initial population. So once the initial population is chosen, we are going to choose the best chromosomes out of it. Okay, so when I have 5 chromosomes taken into consideration, and out of that 5 random solutions, some 2 or 3 might be good one. So we're going to choose the best solution, best parental chromosome out of it. And once after selecting the parental chromosome, we are going to go for the reproduction operation. So the reproduction might be either crossover or mutation. And the last step is once the reproduction is done, you will have some remaining set of chromosomes. The resultant set of child chromosomes will be there. Okay, so that will be the offsprings, and we have to evaluate the offspring. And we are going to repeat this n number of times. Like again, out of those solution, those resultant children chromosome, we are going to choose the best one and choose that as a parental chromosome. Again, go for crossover mutation, and this will go for an n number of iteration. So this is how a genetic algorithm work. So I have taken a very basic, a very simple example, and I'll explain how does this genetic algorithm is working. So here, this is the function that is taken. You're going to maximize the function f of x is equal to x square. So this is a very easy and known function. Just to know the working mechanism of genetic algorithm, I have taken this example, and the value of x here ranges from 0 to 31. So first step here is to choose a particular encoding type. Okay, so we need to, the solution is from 0 to 31. So out of this x value from 0 to 31, one value will have the maximum. Okay, so we are going to choose for which x value this x square is maximum. So this is very basic, like since x square is an increasing factor, we always know that 31 has the highest value. But when we are like the way in which an genetic algorithm can be applied for this kind of problem is taken into consideration. So first step, as I told you, the entire working is going to be happened in terms of chromosome structure, and we are going to operate within the set of solutions. So set of solution here varies from 0 to 31. Okay, so this is the limit, 0 to 31. So one way or one basic encoding type is called binary encoding. So binary encoding is just to convert the values into a binary value. So for 0, binary value is 0, and for 31, 5 ones are used to represent 31. Okay, so here we can take a binary encoding type, but the problem is like for 31, we have 5 ones, and for 0, you have single 0. So one thing that you want to note it down is all the chromosomes should have a same type. Okay, so most of the crossover operations, it goes with the similar size of a chromosome. Okay, the chromosome size should be same for the entire operation. So that is not mandatory. Even some other operating techniques, crossover operations are also there. But still for our application, I'll just choose the length of the chromosome as 5. Okay, since for representing 31, I need 5 ones to represent. So for 0, I can represent the values with 5 zeros. Okay, and similarly it goes. Okay, so when it is value 1, 4 0 followed by 1 single 1. The binary equivalent can be taken into consideration. So this is the first step. I have chosen the encoding type, and that encoding type here I have taken as the binary encoding type. and this is the structure for it, 5 bit of value. Okay, so this is called binary encoding. And second step, as I told you, we need to choose the number of population that we are going to operate at a single time. Okay, so the population size here I have taken as 4. Okay, so this number, like the value of 0 to 31 is, as it is a lesser value. Okay, so it's better to have a smaller number of elements alone to operate. So when you have NS2, it is really very difficult. So I'll just like, it is very simple. So I have taken n value as 4. And the next step is like, we have to choose random population, initial population. So from 0 to 31, randomly we have to choose some 4 values. Okay, since the population size is 4, I need to choose 4 elements out of 0 to 31. And that is randomly chosen. So here for this example, I have taken the value as 13, 24, 8, and 19. Okay, so 3 steps are over. And fourth step is very important, to select the parental chromosome. So as I told you, the parental chromosome, out of the 4 values that you have chosen, we have to choose the best element out of it. Not all the 4 taken can be taken into consideration for the next generation. Only the best chromosome, whichever has the best value, can be chosen for the next generation. Okay, so here I have chosen a method that is called Rowlett-Wheel selection method. Okay, so this Rowlett-Wheel selection method is like, you should have noted as a Rowlett wheel like this, right? So you'll have a wheel-like structure with some values, and you have a small ball, and the wheel is rotated, and wherever position the ball shows, right? So that that element, okay, here the ball is shown at 7, so 7 is the winning component. Similar kind, here we are going to focus, like I have 4 chromosomes, and based on the fitness function, this chromosome is like, the circle is formed. Okay, based on the fitness function, this circle is formed, and we are going to use probability function for calculating the number of times a a string may be chosen. Okay, so that is selected. So that is called Rowlett-Wheel selection method. I'll explain step by step. So this is the initial population we have taken, right? So I have taken the population size as 4, and the initial random values are 13, 24, 18, 8, and 19. Okay, so the corresponding encoding technique is the binary equivalent for it, for 13, 24, 8, and 19. So now we have to choose the fitness function. Okay, so fitness function is nothing but the function that is given over here, f of x value, right? So f of x is equal to x square. So we have to multiply the x value. So this is the x value that is formed over here. Now, once the fitness function is calculated, we are going to project it into the circle. Okay, the Rowlett wheel that we have discussed previously, right? So we are going to project this value into the circle. And as I told you, this is based on the probability. The portion of the circle can be allocated for this corresponding values. So that is calculated using the average and total. So a probability can be given as the value of f of x value for that particular x value divided by the total. So this will give the probability of that, the portion of that particular string going to occupy in this circle. Okay, so here this is the value. So when you calculate the probability of entire thing, that comes to 1. Okay, so this is the corresponding circle for it. So it means that string 1 occupies this blue color portion, and string 2, it has the highest probability, and this occupies the maximum area of the circle. And string 3, it has the very low value, this green portion, it has the very low area, and this is occupied over here. Okay, so now the wheel is ready. What we have to do, we have to rotate the wheel, and we have to check in which place the actual winning point is there. Okay, again we are going to use a probability function for it. There is no exact wheel actually. We are going to use a probability function for calculating this. Okay, so here this string 2, it has the highest probability. Okay, so it can be taken into consideration. So this string 2 has a possibility of getting into more number of times, like it can come in many number of winning points. Okay, so here this is actually calculated based on the expected count divided by average value. Okay, so there are 2 ways in which this value of expected count can be calculated. One is we already know the probability. Okay, and one more thing, we need 4 parental chromosome for working. Okay, so the 4 parental chromosome in the sense like the wheel will be rotated for 4 number of times. So whichever gene has the highest, whichever string has the highest possibility of taking into consideration. So that matters. So one way I can either divide this f of x value with the average, so that will give the same value, or else I can multiply the probability count into 4. Okay, since we are going to do it for 4 number of times, so both is going to give approximately the same values. So this is the value that is given. So this actually means 0.58% string 1 can be chosen, 1.97% string 2 can be chosen for next generation, and 0.22% the string 3 can be chosen for, like when you add up all these things, this will come 4. This means that 4 times the wheel is rotated, and each time, so this is the probability of string 1 to get selected, string 2 get selected, and string 3 get selected. Okay, so for getting the actual count, we don't want the pointed values, right? So we are going to check the numbers. So here we can round off this value. When you round off this value, so this is the value that is actually we got over here. This actually denotes string 1 can be selected once, string 2 can be selected twice, and string 3 it has the lowest probability, and the fitness function is very low, and it has 0% of possibility to get it selected. Okay, so this is the combination that we got. Now what we are going to do, we are going to make this as a parental chromosome. But the problem here is string 2 got selected twice and string 3 is not selected at all. So we have to eliminate string 3. So that is not fit at all. And string 2, the highest fittest chromosome out of the selected parental chromosome. So what we have to do, we can combine string 1, string 2 once, and string 2, string 4 twice. Okay, so we can have 2 combinations. So string 2 will come in both the combination. So this is the parental chromosome that we have taken. Okay, so the next step is the parental chromosomes are chosen. Now we have to combine those two. So the string 2, it has 2 number of possibility. So this can be combined with string 1. So that will form the first combination. And again string 2 with string 4, that will form the second combination. Okay, so this is the first parental chromosome and second parental chromosome combination. So once this is formed, what is the next step? We have to go for crossover or mutation. So please make a note of it. Whenever we are in the starting point, you have so much of crossovers. Okay, the mutation rate is very low. Crossover means you're going to cut the chromosome and mix it up. Whereas mutation is you take a single parental chromosome, modify one single portion, one single gene alone in a chromosome. So that is called mutation. So whenever a generation is started, this mutation rate is very low. So even after n number of iteration, if there is not much difference, okay, if not the optimal, if the optimal solution is not reached, then you're going for this mutation. Okay, so I'll explain the reason later. So now we'll see the steps. Okay, so the next step, fifth step is finding crossover or mutation. So here first we have to denote, we have to take up a single line. So this line is called an crossover point. You can place it anywhere, and from that point, the genes will be swapped. Okay, so here 1100 is combined with next combination. This 1 will be moved up. Okay, similarly, this portion of gene of the second string will remain as it is, whereas this 0 will be moved over here. Okay, so this is again a randomization problem. The crossover point that you have taken is random, any place. And similarly, for the parental, for the second set of parental chromosome, I have chosen the crossover point somewhere after second bit. Okay, again, we are going to repeat the same. The first portion of string 2 combined with string 4, and again first portion of string 4 combined with second portion of string 2. So this will form the children chromosome. So this is the next generation chromosome that is going to be passed. Okay, children chromosome. Now the last step, you're going to evaluate the offsprings. Okay, so here these are the offspring that is formed by the combination of parental chromosome, the corresponding x value and corresponding f of x value. So f of x value is nothing but x into x. Okay, multiply the value of x. So now this is the initial population that we have taken, and here the maximum value of x is 24 and f of x is 576. In the second generation itself, we got 27 and the f of x value was 729. So that is the maximum value that is formed. Okay, so from the first generation to second generation, within one generation, we got a best solution out of it. Okay, so that is the working mechanism of genetic algorithm. So with this offspring from a chromosome, we are going to start it again. Again, we have to go for the selection operation, crossover, mutation, evaluation of the offspring, and we have to repeat it n number of times until the number of iterations are over. So genetic algorithm always guarantees for the best solution. So it won't go guarantee for the optimal solution, but always after each and every generation, it is going to give the best solution out of it. Okay, so this is the working mechanism of genetic algorithm. And one more thing I told you now, like why we have to choose only crossover. The reason is like when you have taken an initial population with like this is randomly chosen initial population. In case if I choose a random population where the first bit of initial population is always zero, if all the parent has the first bit as zero, whatever the combination that we makes, we don't reaches the, we'll never ever reaches the optimal solution. Okay, the reason is this first bit has the highest possibility. Okay, so that is going to define the entire greater value. When the first bit is zero, will never ever reaches to the bigger solution, the optimal solution. So in that case, what happened after some n number of iteration, even if we won't get the best solution, we are going for mutation. So mutation will randomly choose any one bit and they try to get mutated. Instead of zero, it will make it as one. In that case, you have a possibility of getting into a greater optimal solution. Okay, so this is the working mechanism of genetic algorithm. Thank you.